Hi everyone, I'm Amelio, a postdoc at ETH, and today I'm gonna talk about my work, my PhD work in Trento in collaboration with Jacopo, Carusotto and Alessio Chiocchetta, and you find here the references. So the topic is temporal coherence of out-equilibrium quasi-condensates in 1D. Out-of-equilibrium quasi-condensates basically means lasers. Indeed, the motivation, the original motivation of the project was to study how good topological lasers are. Topological lasers are devices that came out a few years ago, and basically instead of having a laser built with two mirrors that form a cavity, the cavity is given by the edge modes of a topological lattice. So you know that for a laser to be good means basically to be coherent, to be monochromatic. We can see this looking at the emission spectra, frequency resolved emission spectra, and basically we want to have a very narrow Lorentzian, so a very small line width, that is the width of the Lorentzian. So since the edge state of a 2D topological laser is a 1D object, first one needs to understand the physics of 1D lasers, and this is what I'm going to present here. And if you want to know more about how this applies to topological lasers, you can look at the papers. So let's start with a model for a laser. So basically, lasing is the out-of-equilibrium analog of Bose-Einstein condensation. Photons kind of condense in a coherent state in the sense of quantum optics. And this coherent state has a well-defined intensity, but as an arbitrary phase that basically is the analog of U1 symmetry breaking of BC. And so in this model we need to have some saturable gain, some losses, and also we will include some external noise that selects the phase of the field. And this noise in practice can be provided by spontaneous emission, thermal fluctuations, etc. So the important thing is how this U1 symmetry affects the dynamics. So we can decompose the field with a complex number of arbitrary phases, but with an intensity that fluctuates as only small fluctuations, and in particular the equation for density fluctuations will feature a relaxation rate. Instead, the equation for the phase has no restoring force and is a random walk. And if we look at the experimental quantity, that is this G1 field-field correlator, you can basically express this as the exponential of the phase-phase correlator in time, and this, because of the random walk, turns out to be an exponential decay. If we Fourier transform this quantity, we get the emission spectrum, that is a Lorentzian, with the line width given by this gamma that was first found by Schawlow and Townes. And the important thing is that this is inversely proportional to the total number of photons in the lasing field. And this is quite natural. The more photons you have in the state, the more noise you need to perturb it. And we can generalize this to an array of laser resonators. Let's suppose we can, so we have some tunneling between the resonator, so if you prefer some Laplacian with some mess. And let's assume that we have a condensate on top of which we can linearize. So a uniform condensate, we can find the linearized modes, the famous Bogoliubov modes. And in this case they will have some real and imaginary part in the frequency. In particular, there is this Goldstone mode that has zero frequency and this reminiscent of the U1 symmetry breaking. But also there are these other modes which are phase-like, long wavelength, and very long-lived. In this linear analysis, the coherence time, that is the inverse linewidth, turns out to be once again proportional to the total number of photons in the laser, that is here proportional to the length of the systems times the density. But we know that in 1D there is no condensate, but just there is no longer range order, so we need to treat this with more care, and so we can still adiabatically eliminate the density fluctuations and have this Kuramoto-Sivashinsky equation for the phase that is nonlinear and will be renormalized by in the RG sense flow sense at a long wavelength, and at long time scales will flow into a Kardar Parisi Zhang equation. Here, you know that the Kardar Parisi Zhang equation describes the growth of interface. Here, the interface is basically the phase, and this describes how well quasi condensate in 1D. And indeed, we know that we know the we know the phase correlator from KPZ theory. That is universal with two exponent z and key, and we can relate this by exponentiation to the G1 field correlator. So the important thing here, what we understood was that we need to reconcile the Schawlow Townes picture that was introduced for a point like resonator basically, and the Kardar Parisi Zhang physics that holds for infinite systems. And for a finite but extended system, we can study this same special point G1 of T correlator. And for small system we have Schawlow Townes physics, so we have a decay of the temporal coherence. For Kardar Parisi Zhang physics, if we look at the same time window, we will see instead a stretched exponential typical of KPZ. And but the important point is that if we can go to longer times, we will recover once again the Schawlow Townes decay. So the first conclusion is that the physics of the linewidth is a finite size effect, if you want to reason in statistical mechanics terms. And the other very important conclusion is that this linewidth is broadened a lot with respect to the linearized Schawlow Townes analysis. Indeed, we see that for small systems, the laser, or the phase equation is the same, will feature a coherence time that grows proportional with the size of the system. Instead, for larger systems, the nonlinear phase dynamics becomes important, and we have this exponent, so the coherence times grows like L to Z minus 2k, that in 1D is the square root of L. And so to conclude, we have investigated this crossover between KPZ and Schawlow Townes dynamics. And in particular, we have highlighted how the phase nonlinearity in the equations gives a broadening of the linewidth. And these results, as mentioned before, can apply also to the 1D edge mode of a 2D topological laser. And here we have the very fun fact that disorder can enhance the temporal coherence, and by suppressing the nonlinear phase dynamics. And I suggest you to have a look at our paper, and also upcoming work in this direction of studying how spatial fluctuations affect temporal coherence, something will come out soon about the linewidth of non-uniform polariton fluids. For now, thank you for the attention.